Okay, so in the last video I introduced you to two more made-up quantities. These physical quantities, we call them momentum and impulse. And like the other made-up quantities that we talked about, like work and energy, they give us a way of keeping account of the system. And so with conservation of energy, it's conserved under certain conditions, whereas conservation of momentum is conserved for other conditions. So I want to derive conservation of momentum with you, and then we're kind of going to talk about when it applies as opposed to conservation of energy. So here's our new accounting. We are in a new currency. Instead of joules, we're talking kilograms meters per second or Newton seconds. So let's look at this interaction. Let's say we have a mass of A approaching a mass of B. A is moving with a velocity of v sub A. B is moving with a velocity of v sub B. These two masses will collide and leave each other. Maybe B has now slowed down and A has sped up. Either way, A is going to leave with some new speed. I'll call it v sub A prime, and this will be v sub B prime. We said shorter, didn't we? Or slower. Okay, let's look at the interaction here. This collision, according to third law, the force of B on A should be equal and opposite to the force of A on B. And we know that the time that B is in contact with A should be equal to the time that A is in contact with B, so that interval there. If these two are the same, then their impulses, so let me just write it like this. We'll use one subscript for the whole thing. Should be equal and opposite. So if they experience equal and opposite impulses, keep in mind impulse momentum theorem tells us that impulse causes a change in momentum. So they will experience equal and opposite changes in momenta. So we get the mass of A ending with A prime, and it started with v sub A. That was a negative, so actually that should be, so it should be final minus initial. We're taking the negative, so we're going to do initial minus final. And over here, final minus initial. Let's say I'm afraid of negatives, so I'm going to add the two negatives to each side. And here, right away, we're seeing, oh no, I left this out. Hey, remember, momentum is a vector. So all this addition and subtraction, we need to keep in mind that the the velocity itself has a direction, so we could be adding a negative, subtracting a negative, adding positive, subtracting a positive. It doesn't matter. We just got to make sure that we're consistent with our coordinate system. But either way, these are the two momenta from the beginning. So in this scenario, we would be adding a to a negative b. And over here, these are the final momenta of the two. If I'm saying to the left is still negative, then we would be adding b to a negative a. In either instance, though, what we're getting at is the total momentum in the beginning is equal to the total momentum at the end. And that's conservation of momentum. It's occurring because the impulse here, that force and time, is internal. It's part of our two-mass system. Okay. And that's one way we can think of conservation of momentum, is as a system. So if I'm looking at the two masses, and if you recall the free body diagram videos I did, we did some as objects, individual objects, and some as systems. So let's refer to this entire system through first law. First law says an object at rest will stay at rest, and an object with a velocity will keep that velocity, unless, or rather if, a net force is absent. So in absence of a net force. Well, we can make some changes here. Instead of an object, we're talking about the system. So the system itself will stay at rest, or will maintain its velocity in absence of a net impulse. The only impulse in our system here is internal. So the momentum it has, so if we treat this as like a box and there's marbles moving around, whatever the box was doing at the beginning, it'll keep doing that at the end, regardless of what the marbles are doing on the inside, provided they don't hit the edge of the box, because that'll shove our box, right? So the system at rest will stay at rest. System with velocity will maintain its velocity in absence of a net impulse. There's no external push here. That's not happening, so the momentum should be the same. Second law. Let me go back to this guy. Second law says the net force on a system is proportional to the acceleration of the system. And if we go back to our thinking there, we're swapping this out for a net impulse. And when we add in the mass, this becomes a change in momentum. So basically, conservation of momentum is saying if there is a net impulse, we'll get a change in our total. So the momentum at the beginning will equal the momentum at the end, plus or minus any net impulse to the system. So this has to be an external impulse. And that's Newton's laws applied to a whole system of objects. And like I'll illustrate that later as a single point in the system, and we'll talk about that later.